Welcome to this explainer. Look, if you've been grinding through the intricate math of thermodynamics, you already know how fast things can get completely overwhelming, right? Well, today we're pulling all of that together into a practical, structured approach based on the source's design information. We're going to look at the exact procedural mindset that engineers use to survive and actually thrive when they're staring down a brand new, incredibly messy heat transfer problem. Let's get into it. Here's our roadmap for today. We'll start with the heat transfer challenge, then explore the art of simplification, move on to tackling conduction problems, decode some convection charts, and finally wrap it all up with the preliminary design toolkit. All right, part one, the heat transfer challenge. So we really have to start by acknowledging the harsh reality of practical engineering. In the real world, you literally never face just one mode of heat transfer perfectly isolated in a vacuum. It's chaotic. Conduction, convection, and radiation, they almost always overlap, interact, and create this highly complex system. Think about it. Most conduction problems have a convection boundary you've got to deal with, and most convection problems actually rely on radiation and conduction just to deliver energy to the surface in the first place. You're constantly juggling two or even all three of these modes at the exact same time.
Now, the author of our source material gives a really strict warning here, and I love this. They point out that this is not just some simple formula hunting cookbook. It's a methodology, and it absolutely requires intuition. See, when you're looking at summary charts and standard equations, it is so tempting to just plug in numbers and play. But as you get more experienced, these procedures do become automatic. For the novice, though, you have to actively resist treating this like a cheat code. You really have to train yourself to think critically about the physical system as a whole.
Moving on to part two, the art of simplification. Okay, so faced with all that overwhelming complexity we just talked about, your absolute first crucial step is simplification. You just have to reduce the number and complexity of the modes involved. And here is a totally counterintuitive idea. Accepting an error margin of plus or minus 20 to 25% in your empirical correlations is actually your secret weapon for preliminary design. I know, right? That might sound absolutely terrifying for a precise science. It's kind of like building a bridge and just hoping you're within 25% of the other side. But the truth is, this basic level of uncertainty is just inherent in a lot of convection empirical correlations anyway. Honestly, accepting that uncertainty is totally liberating. It frees you from agonizing over perfectly exact initial calculations, allowing you to use summary charts to quickly find an actionable starting point. In preliminary design, grabbing numerical values from a chart is usually, well, it's good enough. It points you in the right direction and establishes a solid baseline. Obviously, if you need to run a super rigorous, heavy computer modeling study later on, you'll dig into the complex equations. But you don't start there. You always start with the charts. Okay, let's jump into part three, tackling conduction problems. Our source outlines this really highly structured graphical block diagram for tackling these exact problems. I like to think of this 5-step procedure as a diagnostic checklist, kind of like what a doctor or a mechanic might use to rule out the basic stuff before ordering some crazy expensive test. First, you determine the material properties. Then check the boundary conditions. Is it forced convection or radiation? Step 3, is it steady or transient? Step 4, 1D or multidimensional? And finally, step 5, can you use a simple relation or do you really need a full numerical model? You always begin by assessing the solid itself. You've got to determine the conduction material and its approximate thermal properties right off the bat. Like, does it have high or low conductivity? Is it super dense or is it lightweight? Getting this fundamental first step right is absolutely crucial because it dictates everything that follows in your flowchart. And here's a fantastic example of a diagnostic shortcut in action. Let's say your checklist reveals a transient or unsteady state problem. Well, you don't need to immediately jump into complex calculus. Actually, scratch that. You really shouldn't jump into complex calculus. Instead, if the total heat transfer coefficient times the volume to area ratio divided by the solid's thermal conductivity is less than 0.1, boom, you can just use the lumped capacity approximation to easily figure out how the temperature is going to change over time. It is a massive time saver. Right, let's shift gears to part 4, decoding convection charts. So after assessing the solid, we transition to fluids in motion. Now, the source gives us a wealth of charts for this, but listen up because they come with very strict rules of engagement. A foundational rule when calculating convection is that you must strictly use the heated or cooled surface area that is physically in contact with the fluid. Do not use the flow cross-sectional area, or you're going to make massive errors.
The text specifically highlights this because it is such a common, catastrophic mistake. Remember, the cross-sectional area is for figuring out the mass rate of flow. The surface area is for the actual heat transfer equation. Mix those up, and you'll completely ruin your design.
The charts also remind us just how critical it is to evaluate fluid properties at the precise, correct temperature. You really have to pay attention to whether a specific chart requires the film temperature or the average bulk temperature. But there's a fascinating little caveat here. Ideal gases, like air, actually give us a bit more leeway than heavy oils. For an ideal gas, you have considerable latitude in your temperature property determination without totally throwing off your final convection coefficient. But for viscous liquids or petroleum products, no way. You need absolute, strict precision there.
This perfectly illustrates exactly how engineers map out convection data. Notice how they use both linear and logarithmic scales, depending entirely on the vast ranges of the data they're handling. For something like local Nusselt numbers on flat plates, a linear scale is often perfectly fine. But the source points out that for certain free convection correlations, like isothermal horizontal cylinders, for example, the data can span 20 orders of magnitude. 20! In cases like that, you absolutely need logarithmic charts to make any sense of it.
When you get down to specific geometries like turbulent flows and smooth tubes, you can rely on classic empirical relations, like the Ditters-Boelter equation. Notice how logarithmic charts can map the Nusselt and Reynolds numbers to make things manageable. For this specific system, the text emphasizes that you must evaluate your fluid properties at the average bulk temperature. And, amazingly, if you're stuck without other data, you can even apply these relations to non-circular flows, just by swapping out the physical diameter for the hydraulic diameter. Pretty cool trick, right? Finally, Part 5, the Preliminary Design Toolkit. Let's pull all these fragmented flowcharts and graphs into one cohesive perspective. By transforming all that intimidating math into the structured survival guide, engineers can quickly and confidently triage a thermal problem to get a reliable preliminary design. You simplify the overlapping modes. You use your procedural checklists to assess the solid and the fluid. You make sure to use the right areas and temperatures. And most importantly, you embrace that plus or minus 20% uncertainty of empirical charts so you can get rapid, actionable numbers way before you ever boot up a complex computer model. I'm going to leave you with a final thought to ponder about the evolution of engineering as a whole. If these preliminary charts can reliably get us 80% of the way there, what mysteries are really left for the heavy computer models to solve? As you continue your own journey into heat transfer, keep this survival guide handy, trust those procedural checklists, and never, ever stop asking questions about what the data is actually showing you. Thanks so much for joining me on this explainer, and keep learning.